You may be puzzled by the fact that the lighting on for this session is brighter in more daylight than the previous session and the next session. And the reason is I had for the first time, it puzzled me. For some reason I could not cut with using Microsoft's Movie Maker. That's the software I usually use. Once I take the raw film from the Handycam and then I download it into my laptop and then I process it using Microsoft Movie Maker, and I cut it. It's usually about half an hour or so per session, and I cut it into 2, 3, 4 pieces. But for some reason I wasn't able to do that, and all the other clips I was able to do, but for this particular one I just couldn't do it. So I tried everything I tried, didn't work. So eventually I just decided to do it again. Now I could open it and look at it on the laptop. It was only when I got into Microsoft Movie Maker that I had the problem. So I was able to just put it on the screen, and I just copied it. I just copied out the text again. So this is version. Well, it's the same version, but it's attempt number 2. So all right. Well, I'll continue on there. So your wave number k now is a vector, so it's in 3 dimensions. So it's a wave front moving in a particular direction, k. Okay, and this wave vector now is perpendicular. Here's your wave front. So imagine this plane here. That's your wave front advancing, a free wave, if you like, and this is your wave vector now, 3-dimensional vector. Right? Now, so using the formula we just had in the previous session, you now get finite, less than infinity, finite answers, and your probability density is now just 1 over L cubed. You may ask, well, what does that mean in 3 dimensions? In 1 dimension, you have this sort of cyclic property of x equals x plus L. You can look on this very long circumference L as a finite length, effectively a straight line. Topologically, it's pretty much a straight line, but it's looped. So in 3 dimensions, where do you get this probability density of 1 over L cubed? Well, to find the actual probability in a given volume, 3 dimensions, that would be like a triple integral. Probability density integral dx, integral dy, integral dz, and for each dx, dy, dz, your integral limits will be between 0 and L, 0 and L, 0 and L. So you'll just get this 3 times, right? So hence L cubed, right? And that's constant. So that implies the particle's equally likely to be anywhere, right? So a free particle, right? Now. Getting on to, we can now actually use the theory of the free wave, the free particle, free wavicle, and shoot, in a sense, this free wave at a barrier. And then we can start solving Schrödinger's equation, the STI, Schrödinger time-independent equation, for these kinds of problems. And the barrier we'll start with, we'll let it have a finite potential, V0, and there are various cases, like when the incoming energy, the free wave, if it's wavical, if it has energy E that's larger than V0, less than V0, equal to V0, pretty much, various cases, we could allow our barrier, the potential barrier V0, to be infinitely thick. We could imagine it being very thin, so that perhaps the wave the wave function then, once it's in the barrier, it'll start decreasing exponentially. But if the thickness or the thinness of the barrier is small enough, maybe that exponential decrease will not take the wave function down to zero. It will still be finite when it hits the other end, the other edge of the barrier, and then start waving again, start oscillating. That kind of phenomenon called tunneling, and that'll be in a future session, second half of the board. Right. So we're going to start talking about you're sending a free wave into a potential barrier, a potential step, right? And wondering asking the question, how does it scatter? I mean, how does what happens to the wave? Does it all go through? Does all of it bounce back? Does some of it go through? Some bounce back? If so, what proportions? Blah blah blah. Yeah, those kinds of questions. Right. So how to start? Go back to chapter 1, lecture 1, and have a look at the theory we did on the idea of flux. What is flux? Sort of the current. If you look upon the probability as a kind of elastic fluid, then the fluid's sort of flowing over space and time. At a particular point in space and time, the probability there will change. So you think of it as a kind of fluid. The fluid's conserved; it doesn't disappear. I mean, increase and decrease in density in different places, but it doesn't disappear. It's conserved. Okay. So flux then would be, if you're thinking of volume, the flux then would be how much of this probability fluid, if you like, or flux, flows in and out of that surface. Or if you're in one dimension, just draw two edge points, if you like. So you're talking about a region with start point, end point, and here's your region. So your flux would be like the flow, probability flow in and out of that region. Okay, so hence it's called flux. Now we actually derived a formula for it in chapter 1. So go back and revise, and I've written it out here. Although actually it's not quite the same. This is now the three-dimensional form. What's different about it in chapter 1 in the one-dimensional form, instead of having this del that's sort of an inverted triangle pointing down, it's an operator, three-dimensional operator called del, D-E-L. Before you had d psi by dx, and here d psi star by dx. The star, remember, that just means the conjugate. Conjugate means that you whatever psi is, wherever it has an I, square root of -1, an I, you replace the I by minus I. It's as simple as that. Okay. So if you've not done any vector calculus, you may have a bit of a problem, knowing what this del is. Now I've given you the definition here, a bit of a crash course in a part of vector calculus. Now I've convinced myself I should. These vector calculus type things keep popping up. So I'll teach a course on undergrad vector calculus. I've made that decision now. I will use the textbook in the Schaum series of textbooks, SCHAUM. There's a very good one on vector calculus, and I have it in paper, but it's buried in book boxes, hundreds of them, in cold storage, so it's not accessible. So I'll just download it. I probably have already, and put it into my iPad, and then just use my iPad to write up the vector calculus wording on the board, on the whiteboard. So vector calculus talks about things like this del, usually called grad, short for gradient, div, that's short for divergence, and curl, which is a quantity that measures how much a vector field bends or curls. Right? and other things like del squared, which is the Laplacian, talked about in an earlier lecture. Various famous theorems involving integrals in vector calculus. Gauss's theorem about the flows in and out of a surface, Stokes' theorem, and so forth. Yeah, but it's a whole course. Anyway, so this del psi, or